In previous attempts, I designed and tested a spring-weight gearbox for the floating bar mechanism, but unfortunately, it failed. The gearbox could not lift a 500-gram bottle with a 16cm bar. As a result, I am now considering using the backup plan, the bell reduction, which is similar to the original Voron 2 ZXX. I wonder if this bell reduction setup will work for my application or if it will also fail to lift the bar. Hi, welcome to Slow Engineering. I'm David. The bell reduction unit is similar to the ZXX mechanisms on the Voron 2 printer. This model also utilizes an 80-tooth and 16-tooth pulley to create a 5:1 ratio reductions for increasing the torque. The 80-tooth pulley is positioned between the bearing housings and connects to the 16-tooth pulleys on the stepper shaft using a 188-tooth loop belt. The distance between the two shafts determines the tensions in the belt, which can be a bit tricky to assemble but is easy to understand. Ensuring the proper tension guarantees that the two shafts are correctly spaced. The output shaft will undergo a series of torque tests with the 16cm bar as the load. I begin with a 500-gram water bottle and a 16cm bar capable of producing 0.785 Nm of torque. The stepper had no trouble lifting the bottle. Then, as I gradually increased the water weight to 600 grams and 700 grams, I noticed that the stepper struggled to lift the 700-gram bottle. With more detailed measurements, I continued testing with weights between 610 grams and 700 grams to determine the reduction unit's capability. The maximum weight the unit can handle is 690 grams. In addition, I adjusted the control code and increased the RMS currents from 1.4 amps to 2 amps. As I had misunderstood the spec of TMC2209 in the previous test with the spring-weight gearbox, increasing the current also increased the torque, but the final weight limit remains at 690 grams. With the weight and the bar length, I calculated the unit's torque limit to be 1.083 Nm. After conducting the spring-weight gearbox test, I redesigned the bar mechanisms in the previous episodes to make it lighter. I aim to create a lighter mechanism that could lift the bar using the reduction unit. Additionally, I can now calculate the total weight of the bar more accurately, taking the weights of screws, inserts, and 3D printed parts into account based on the design. I am also considering using different materials for the 3D printed parts, which may result in slight variations in weight. The weights for each component can be estimated using the material properties of the 3D software. Or the length of the filaments calculated by the slicer, along with the filament's density to determine the final part weights. The DIN rail for the 350 version of the Voron 2 needs to be 409.6 mm long. According to the 3D software calculations, the weight of the rail is approximately 51 grams. The combined weight of the screws and thread inserts is 63.6 grams. Additionally, the optical switches on the bar weighs 30 grams. But the 3D printed parts start with the carriage on the bar mechanism, which will be made of I-180 materials from EGOS. This materials has a density of 1.21 and weighs about 2.73 grams. Then the junction parts, weighing 21.35 grams, will be made from a different material, the P150, for improved stabilities and strength to support the DIN rail. This material has a density of 1.4. The remaining 3D printed parts will be made from ABS due to its low density of around 1.05 and its ability to meet temperature-resistant requirements. These ABS parts include 5 ducts and 4 spacer plates and a 350 version Voron 2, with a combined weight of 112 grams. All the components on the bar mechanism sum up to a total weight of around 1.33 kilograms. In the previous episodes, I calculated the torques on the floating bar to estimate the needed torque for the reduction units. However, after designing the floating bar in details, I realized I had made another mistake in approaching it. The purpose of these two reduction units is only to drive the belts and pull the bar up and down. So I need to care about the weight, not the torque. The model is unlike the bar directly attached to the reduction unit output shaft. The reduction unit will have a 20-tooth timing pulley to drive the belts. By considering the pulley pitch diameters and torque limit values, I gained insight into the supporting force of the belts. The pulley pitch diameter measures 12.732 millimeters. And when combined with the torque limit of 1.083 Newton meters, I calculate a pulling force of 170.123 newtons through the belt. This force is ample for lifting the floating bar without any issues. Even without the reduction unit, the stepper should be able to lift the bar. Therefore, the SRAM-weight gearbox should also be capable of lifting the bar. You may be wondering about removing the reduction unit at this point. However, the bar weight is not the solo for the belts, as the tool changer system utilizes magnets to engage the shuttle and tool heads. Disengaging the tool head from the shuttle will also require force, and the required force is in the same direction as the weight. I experimented to determine the force required to disconnect the tool head. I created two parts to simulate the distance between the two magnet placements and used varying weights to test the magnetic connections. I found that at 1.4 kilograms, a slight shakings would detach the parts, and with a 1.45 kilogram water bottle on the ground, pulling the upper part upward would separate the two parts. This indicates that I will need to apply a force of 1.45 kilograms force to disconnect the shuttle and tool heads. Is the connection too strong? Please leave a comment to share your thoughts. With the detaching force for tool heads and the bar's weight, the two reduction mechanisms provide a total force of 2.78 kilograms force to support the floating bar mechanism operation. Two steppers can still operate the systems without the reduction units. Therefore, the main advantage of the reduction units is not weight but rather the increased resolution. I'm surprised that the weight doesn't need the reduction units. However, I may have missed something important again. At least the entire concept looks okay, and the powerful reduction units leave the potential second bar of tool heads for more flexibility. As always, moving forward.